And now if I go to, and if I go to here, can you see my slides?
Yeah, fantastic.
Let me just see if a
Yeah,
certain,
yeah,
is
it's
video working
also
okay?
changing. Yeah, it's also changing. Fantastic.
Okay, excellent.
So we wait for another 5 minutes because it's just 7:25 p.m. here for
Sure,
the participants to join, and then we'll start. Thank you.
that sounds great. Thank you so much.
Okay, so Faizan, I think we are good to go. Shall we start now?
Yes, sir, we can start now. There's already around 30 students are here.
Yeah, so please, comments.
Okay,
Okay,
so
sound. Oh, sorry. Go ahead. Yeah, sorry.
Yeah, yeah. Just give us 2 minutes to introduce you.
uh,
Uh, so, good evening, everyone, and good morning, Russ, as per your time, I believe. Uh, we are fortunate enough to have Professor Ruslan Salakhutdinov to deliver this plenary lecture at this session of Winter School on Deep Learning. Let me briefly introduce Ras, whose works you are not only have you read about them, but many of you might be using such groundbreaking contributions that he made during his early career. So Professor Ruslan Salakhutdinov completed his PhD in machine learning at the University of Toronto in 2009, following 2 postdoctoral years at the MIT AI lab. He became an assistant professor at the University of Toronto in the departments of computer science and statistics. In February 2016, he joined the machine learning department at Carnegie Mellon University. Renowned for his prolific publications in prestigious conferences and journals, and also his really groundbreaking and influential contributions to the early developments of deep learning. Russ specializes in probabilistic graphical models, deep neural networks, and large-scale optimization. I think most of you have heard of Dropout and might be using Dropout and deep Boltzmann machines and things like that Russ developed in his early day papers. His primary research objective is to comprehend the computational and statistical principles necessary for uncovering patterns in vast datasets. Russ serves as an action editor for the Journal of Machine Learning Research, JMLR, and has been a member of the senior program committees of notable conferences like NeurIPS and ICML. He has received numerous awards and honors, including being an Alfred P. Sloan Research Fellow, Microsoft Research Faculty Fellow, Canada Research Chair in Statistical Machine Learning, recipient of the Early Career Award, Researcher Award, and Connaught New Researcher Award, as well as the Google Faculty Award and NVIDIA's Pioneers of AI Award. Additionally, he holds the title of Senior Fellow at the Canadian Institute for Advanced Research. Russ's impactful contributions have significantly advanced the field of deep learning as it is today. So with this brief introduction, let us set the stage for him to deliver this very interesting lecture. So Russ, now the stage is all yours. Thank you.
Okay, thank you so much. Thank you so much for the invitation, and thank you so much for giving me the opportunity to talk about some of my recent work. I'd like to talk to you about embodied AI and physical AI and virtual AI agents. This is something that I've been working in the last few years, and today I'm going to talk about that topic. But before I start, given that this is a summer school, I just wanted to show you that, we've seen enormous success of enormous success in the space of computer vision. Our model is just getting better and better. Speech recognition, planning and reasoning. We'll talk a little bit about this. Language understanding, robotics. Right. So we see a lot of amazing thing happening in just the last few years. Part of what's been happening, even over the last decade, is this notion of machine learning plus data. Data becomes one of the critical components for a lot of advances that we see today in perception, 3D scene understanding. I'm sure many of you have sort of seen examples of Vision Pro coming out of Apple. It sort of has a very good notion of 3D scene understanding. Conversational agents like, models by GPT, machine translation, recommendation systems, and so forth. And what's interesting is that if you look at the trends in AI and machine learning today, really sort of, we're seeing rapid progress in computer perception. We're seeing amazing progress in language understanding with the use of large language models and conversational AI. We're also seeing a lot of examples of large-scale self-supervised learning and multimodal learning, something that we'll talk about today. And of course, there is a lot of work on robustness, bias, fairness, and explainability. And, there's also huge commercial investments in AI, particularly in the space of generative AI, large language models, in AR, VR space. There is still a lot of work and commercial sort of investments happening in the space of self-driving cars and robotics in particular. And of course, we see examples of AI for public health, AI for drug discovery, for environmental sustainability. And, given the rise of these models, privacy becomes one of the important research topics as well. And just to show you, this is a slide that I use. It's sort of old slide, but if you sort of look at the kind of generative models we were building in 2014, this is what the generative models look like, and sort of the progression up in 2017, and now with diffusion models, these models are so much better. The progress has been, pretty incredible. This is sort of one of my favorite papers. Cycle GAN was using generative adversarial networks to basically build generative models of zebra-given horses. So it's like a translation from, English to French. You're translating horses into zebras. And obviously, one of the things that we're seeing today is the reuse of large-scale pre-trained models, right? We're seeing it with LLMs. We're seeing it with perception, with the latest sort of perception models. Here, you're looking at the ResNet model, which is a pretty good model for understanding images. And you can sort of, use these pre-trained models, and then you can adjust these models to, for example, doing caption generation and so forth. That's something that's been happening in our community over the last few years, the rise of sort of having these pre-trained large-scale models that then you can adapt for different tasks. And of course, we're looking, probably all of us have now heard about OpenAI GPT-4. It can do, amazing job at question answering, information retrieval, code generation, sort of, solve a lot of tasks for you. And of course, also with the rise of diffusion models, right? The models like DALL-E and Midjourney and Stable Diffusion, sort of the ability from caption to be able to generate images is pretty remarkable. And this was a big advance in AI and machine learning. But today, what I'd like to talk to you about is I'd like to talk about a specific area called object navigation using self-supervised active learning and instruction following. In the first part, in the second part, I'd like to talk to you a little bit about the new trend that I'm seeing, which is sort of, evolution of the large language models is autonomous AI agents. Okay, and the two are sort of aligned together. So let's talk about physical intelligence, right? We're seeing a lot today on the virtual intelligence, right? It's again like GPT-4, but when we think about physical intelligence, we think about agents, and we think about robots interacting in the environment. Right, the robot or the agent observes the environment, and let's say the robot and the agent takes action. So let's say now case actions are going to be navigation, moving around in the environment. So the agent needs to move around the world physically. What's interesting about these settings is that the actions, your current actions, will affect future observations, right? And it would require some form of spatial and semantic understanding of the world that you are interacting with. And sort of one of the common ways of training these models are using reinforcement learning. Or you can think of it end-to-end reinforcement learning, where given the observation, given the goal where I need to go, what I need to do, I pass my observations through some deep neural network. My deep neural network gives me actions. In this case, let's say these are 3 discrete actions, and occasionally I get rewards, positive and negative rewards. And the idea behind reinforcement learning is you get positive rewards. You're basically saying, well, change my actions in such a way that I get more positive rewards, and change my actions so that I don't get negative rewards. And typically in what's called goal-conditioned reinforcement learning, in this case it's goal-conditioned navigation, I can actually give you the goal of what you need to do. So for example, I can give you an image and tell you, find me this image in the environment. And the agent has to execute a series of actions to find that specific image, or object goal, or language goal. And what's interesting, language goal is becoming more and more dominant, because it's convenient for humans, has the notion of compositionality. And ultimately, this is where, I can give an instruction to my agent of what it needs to do, right? And a lot of recent work is sort of processing language goal by using large language models. So we'll see some examples of that. Okay, here's a robot that we've built at CMU. So what you're seeing here is you're seeing observation. This is what the robot sees. Here you're seeing what we call the predicted semantic map. You can think of this as sort of mapping the environment of where things are. And my goal here is to find potted plants. So the robot is over here. It needs to find the plant which is over here, right? And it's a new environment, and so the robot sort of moves around, it processes the input, it builds the semantic map, and eventually gets to the potted plant, right? So this is just one example, and of course, the entire stack of visual understanding, planning, as well as navigation, executing low-level actions is running on the little robot. And one of the things that we've been thinking a lot about is how do we build sort of visual systems that are specifically designed for embodied AI, embodied data. And the reason why is if you look at static images on the web, static internet data, a lot of images look like this, right? And people would segment those images and would use those images for, let's say, training perception models. But if you look at active embodied data, what we call the data that's coming from a robot, it sort of looks like this, right? Obviously, there is a persistency through time, persistency of objects through time. And the data typically looks fairly different from your standard internet like data. Right. And so just to sort of say, well, if we build state-of-the-art, let's say, detection systems based off the internet data, a lot of times we do see, false positives. So here's the robot navigating in an environment, and it thinks it's a chair, right? Or here, if we're looking for, in this case, if we're looking for the toilet, we're missing the toilet because the toilet here is occluded, partially occluded, so the robot just doesn't recognize it. And generally, it is the case that, when we look at the data itself, there is a persistence of objects through time. And people have explored this notion of persistency of objects through time. And it's a very good learning signal because, if you're seeing a couch over here, you're supposed to see it here, as well as here, as well as here, right? Couches just don't disappear. And so this is a particularly important signal that you can use for actually improving perception systems of these robots, of these agents. So let's see how we can do it. There is a sort of a very good notion of what's called action perception loop. And the idea here is that in step one, you're going to be doing self-supervised active exploration. So you can think of self-supervision basically means that there are no additional labels. So you can think of the agent or the robot, you put the robot in your house and it explores the environment on its own without any supervision from humans. And in the second stage, the agent can do self-supervised visual learning. So based on the exploration, the agent can then learn more about the environment and create its own labels to do the learning, right? And so what's interesting about this system is that a lot of systems prior to this notion of active exploration is that you typically, I give you a bunch of labeled examples, you learn the perception model, right? Just like from static environments. But this is the environment where you actually have active environment, where the agent takes actions and move around the environment. And by just ability to take actions and exploring the environment, you can actually improve your perception system. So that basically means that the robot can essentially do learning on its own. Right, and that's a pretty powerful concept, from the fact that you can actually learn on your own without requiring extra supervision, let's say, from labelers or from humans. So let's see how we can do that. The way that we've been approaching this problem is through, again, setting up these two phases. The first phase is active exploration. So the agent takes, it has an observation. We run it through some, let's say, detection system. So we're using Mask CNN, which you can think of as a model that basically allows us to detect objects in images. Once we have this detection, we're going to be building what we call the 3D semantic map. And you can think of semantic map as sort of a map that allows us to figure out where different objects are and which volume they occupy. And we're actually learning the policy through reinforcement learning, and the policy that's maximizing a specific reward that we call gainful curiosity. And then based on that policy, you're taking actions. So there's this notion of, it's essentially reinforcement learning policy where we're trying to build a 3D semantic map as accurately as we can, okay? And then the second phase, what we call the perception, we're going to be using what we call 3D label propagation to essentially create labels based on the 3D semantic map, what we call the pseudo labels or labels based on the exploration policy. And then we're going to be training our own perception model to improve based on those labels. So you can think of this reinforcement learning agent that moves around as a way of potentially collecting label data. Okay. So how do we build this? So how do we do 3D semantic mapping? So the 3D semantic mapping happens as follows. We have the depth, we have the RGB, and we have a sensor reading. Sensor reading can think of X, Y coordinates. We go through Maskar CNN. We get the semantic predictions based on the visual input as well as the depth. We do spatial transformation to get the geocentric view of our map. So this is just because we have the depth, we can get the voxels. And then there is the aggregation, map aggregation. The agent moves around, we aggregate what we're seeing in the semantic map. Okay, so there are a few sort of moving pieces here and there. Some of these pieces can be learned and back propagated, but the idea is that, again, this sort of gives us a notion of building a 3D semantic map. And this is how it happens. As the agent moves around, this is sort of a virtual environment that you're seeing here, based on habitat environment. And this is the 3D semantic map that the agent is building, right? So you sort of have a few objects, and this is what that looks like. Now, the question is, how do we train the policy? Because the agent has to take actions, turn left, turn right, go forward. How do we build an accurate policy so that we can explore the environment as well as we can? And what we do in this case, looking at these voxels, we're summing these voxels up with confidence of 90%. And that now count becomes the reward function, right? And this is the reward function for training the reinforcement learning policy. So we call it gainful curiosity reward. We're essentially training to maximize gaining definitive knowledge of the environment. So this basically allows our policy not to stay in one room and just, spin in one room and not really explore. We're actually saying, hey, move in the environment. Try to, using Maskar CNN or sort of detection system, try to find as many reliable voxels as you can. Okay, and that particular reward signal allows us to build pretty decent policies of trying to figure out where the objects are. Okay, so now the question is, why do we need this 3D semantic map? What uses do we have for it? And that goes to the second phase of the perception, right? This is 3D label propagation. So imagine a situation where I have an observation, right? This is where the robot is. This is the robot looking at the environment, right? What I can do is I can look at my 3D semantic map, and I can use and I can get instance labels by essentially doing ray tracing based on my agent's pose. Because I know these objects should be in the environment. And given that I know what these objects in the environment, I can actually map that back into the pixel space. Right. So I can sort of say, well, here's the potted plant, this is the chair, this is the couch. Okay. And now what happens here is if I look at my perception model doesn't recognize this chair, right? It doesn't recognize this couch. because my perception system is not, might not be perfect, but you're sort of seeing that these are false negatives. They should be here, but they're not there. And the reason why this happens is because I've explored the environment. So I actually saw this chair from a different viewpoint. And because I saw this chair from a different viewpoint, I can map it onto my 3D map, and now I can create labels. And the same sort of happens in, in another setting where, for example, model thinks it's a chair, but it's not a chair, it's a table, right? And so I can get these false positives. And now what I can do is I can train my perception model based on these pseudo labels. So this notion of understanding the environment and seeing objects from different viewpoints allows me to fine tune and actually, train a much better perception system, right? And this is all without any supervision signal. It's the supervision really comes from self-supervised exploration. And this is sort of a setting that where we're seeing there's been a lot of work on, if I take a standard detection system, right, I can do detection and segmentation. There's been a lot of work on using sort of different ways of, optical flow and other things to try to improve these models. And through self-supervised learning, we can actually do much, much better. Of course, this is still far from human level performance. Humans, get the accuracy of about 90%. But this sort of shows that, by scaling these systems up, these models can potentially learn on their own. And here's what, again, the system looks like. This is actually a physical robot moving around in the environment and mapping your environment, right? And so this becomes important because I think that in the future we're going to have robots in your homes or in the places where you live, and they will be able to move around and they will be able to, do various tasks for you. The other thing that you can do is another work that we've done with Apple research is this notion of self-supervision with location consistency. So the idea here is that if you have a robot, the robot can look at the environment from different viewpoints and essentially say, I want those representations to be similar. So you can sort of use what we call contrastive unsupervised training to essentially, based on the location consistency, I'm basically saying learn your representations where the representations of all of these images would be the same, just because they are in a similar location. And this is what kind of like the system looks like. This is the actual physical robot moving around your house, and it's sort of building the map of the environment. And you kind of like seeing these black rectangles here. It's sort of blocking people who taking the videos, right? And so again, the agent sort of takes the action. It moves around here. It's looking for a bed. I think it's trying to get into the bedroom. And this is, again, a completely new environment, completely new house. And the agent essentially moves in this environment and finds the bed, right? Just as an example. And then these kinds of systems can be extended to this is becoming more and more dominant. And again, I'll show you some more of these examples where instead of me giving you goal, like finding the bed, I actually give you instruction. An instruction here could be drop a clean pen in the table. So there is a language parsing. You can use large language models or any other sort of tools to go from instructions to subtasks. We can think of this as a plan or executing sub-goals or subtasks. You can think of it as a high-level plan of what you need to execute. There is a semantic search policy, which essentially, figures out what steps you need to take. And then there is a semantic mapping where, whatever I observe builds the semantic map, and then again goes to the semantic search policy. And the semantic search policy, determines what it needs to do and goes into the policy to execute actions, right? And again, I'm not going to dive into, too many details, but we see more and more systems where I give you an instruction, it goes through some language parsing. You have the visual representation that goes through the visual processing. In this case, we're building the semantic map. Both of that information goes to the agent to execute actions to actually find or complete the task. So just to show you an example, let's say I give you an instruction. This is all done in simulation for now. Give you an instruction of place a cold lettuce slice in a waste basket. And this is what the agent does. It sort of, figures out a set of sub-goals. It executes a set of sub-goals. It builds the semantic map where the knives, where, different objects are. And eventually, through a series of actions, it, completes the task. And it's interesting, these environments are just virtual environments because it's easy to test these systems and train these systems in virtual environments. But just to give you an example, just because I'm giving an instruction of placing a cold lettuce, cold lettuce slice, I actually have to, take the lettuce, put it in the fridge, take it from the fridge, and then throw it away, right? So this is just an example of, the ability of systems to really understand the natural language, right? And again, this comes down to this notion of building intelligent agents, agents that can navigate autonomously, that can localize at plan, that can understand multimodal input, that would include language and vision, perhaps speech, obviously perception of human speech, reason and understand the natural language and recognize objects. So ultimately, in the near future, we're going to have more and more of these agents, physical robots that can, explore, navigate, and execute a series of actions. Okay. Now, in the second part of the talk, let's dive into, so far we've been talking about physical agents, physical AI, robots that actually navigate in the real world. Now we're going to look at what we call virtual agents. So you can think of them as agents that operating on your computer and trying to, help you accomplish tasks on your computer. Okay, so this is, focusing on autonomous agents. And, I've said before that large language models have been very impressive generative models, right? You see from, understanding, generating code. We're going to be seeing more and more these sort of large language models used for search, retrieval, and lots of different applications, right? And so when we look at LLMs, they do a lot of interesting things. They do in context learning, they have zero-shot abilities, they can generate long coherent text, they sort of have some notion of the world knowledge, they can sensitive to the word orderings and so forth. So, one of the things, we've been thinking about how to ground these models to a visual representation just based on large language models. Because large language models, they typically operate just on language. So how do we ground them to images? And this is one of the examples of what we call a model that we've developed called generating images with large language models. And what's interesting about these models is that we're going to have systems that not just generate the text or given the input like GPT-4V, given the visual input, generate me the text, but also models that can generate images through the interface, right? So here, I'm saying that, I'm giving you this image and say, how can I make this more nutritious? And the system would generate, you can add more vegetables and so forth, and then it would generate the image of what it would look like being more nutritious, right? And so kind of, systems that can interact with you, but also with the visual inputs and visual outputs. But what's interesting is that evaluation of these models becomes very challenging, and especially when we go to models that can start taking actions on your behalf, then evaluation becomes very interesting. And that gives us to this notion of, again, I think of this as the evolution of large language models. It's the next state of evolution of large language models. And you can think of many productive tasks that we perform today are actually done on the computer, right? And a lot of these tasks that we're doing today are done on the web. And there's a lot of opportunities to automate these sort of routine tasks, and we're hoping that, this sort of way of automation can augment human capabilities. Let me give you some examples. This is an instance of setting up AWS instance, right? So it's Amazon trying to set it up, and the interface is really hard. My students complain a lot how to set up, AWS environments so you can, fire up your training procedures, for example. Why can't we have AI agents that will just go and set it up for you based on your instructions, so based on your objective? Or if we look at Excel or Google Sheets, there's pretty much, much of the work today that we do is a lot of it is operating on Excel spreadsheets. You'd be surprised. You go to any business, a lot of operations happen on, Excel or versions of Office, right? Open Office or the Microsoft Office has been dominant sort of products. And the question is, can we automate some of these tasks that humans are doing based using these agents? Okay. And let me show you one particular example. An example of what's called WebArena. It's probably most realistic web environment at the moment. It collects websites from popular categories like Reddit, GitLab, and like a GitHub and Amazon. It's self-hosted. It's open sourced re-implementations essentially, and the data comes from Amazon, Reddit, and GitHub. And what's interesting, I'll show you examples of what that looks like, but what's interesting here is that a lot of tasks that humans are doing are not very difficult. It's like 80% success rate, but difficult for language models, for large language models. Even models like GPT-4, they can only, succeed in about 14% of these tasks. One caveat of the WebArena, which was developed in 2000 and last year, but one sort of disadvantage of this environment is that tasks are designed to just use text or HTML source code. And just using text and HTML sometimes becomes very, very difficult. And what we've been building, what we call a VisualWebArena to benchmark and track performance of multimodal agents. Right, so we've been sort of, and this is something that just came out a week ago. We're designing these visually grounding tasks to test the abilities of these multimodal agents. And we're also relying on visual inputs, as well as visual outputs, to find these interesting and realistic tasks. So the environment itself contains of one-stop shop, which is a clone of Amazon Reddit environment, and OS class, which is, you can think of it as like a Craigslist where you can, post different things. And then, this is how they look like. And then we give, the specification. So for example, I can give you a setting of buy me the cheapest color printer and send it to Emily's place as shown in the image. And the image sort of shows, the address where it needs to send. And so, or help me make a post selling this item at $10 less. So let me show you how it looks like. This is what the environment looks like. And this is the agent autonomously has to go through the sort of web interface, find the cheapest colored printer, fill in the information to send it to a specific address, place it, and then place the order. Right now, imagine a system that basically does all of these things autonomously, right? And that's sort of the goal for the agent. Here's another setting, interacting with something like Craigslist, where you're looking for the bike between certain prices, you're finding the bike, and then you're making an offer. And you're making an offer for, buying a bike for $385, right? And so again, there's a lot of work that these agents need to do to sort of, fully complete these tasks. Okay, so how does the setup? The setup is the same as what we've seen in the physical AI agents. It's an MDP environment, Markov decision process environment. We have states, right, which is our observations. So observations could be visual observations, such as the websites, images, or HTML, or there is something that's called accessibility tree, which is sort of, a better version of HTML. It's sort of a little bit cleaner way of representing the data. So you have observations. That's what you observe. You have a set of actions. Remember, in the previous part, our actions were, turn left, turn right, go forward, sort of physical actions. Here, the actions would be click on a particular element or type a particular text in a specific element. Press, a key combination. Close the tab, open the tab, go to a specific URL. So I can just say, get me to this specific URL, go back, go forward, scroll up, down, or stop. Stop basically means I found the answer. Okay, so just like we've seen a setting in the physical AI, it's the same setting that happens in the virtual AI, right? And again, except for me taking actions of move 20 centimeters forward, turn 20 degrees right, here I'm just basically saying click on this button or type this in a particular button. And then the transition function, that given the state and the action that I take, I get to the next state, right? Or I get to the next observation. We have deterministic transition function, and then there is the reward function. And you can think of reward function as basically telling us, have you achieved the task? The reward function that we've seen in the previous talk on the physical AI is if I give you, find me the potted plant, once I'm near the potted plant and I see the image of potted plant, I say, okay, I get positive reward. The reward function here is essentially has the same structure, which is if I take a particular state and so take a particular action, I end up in a particular state, and that's the state I want to be in. I've solved the task, then I get positive reward. Otherwise, I get, if I don't solve the task, I get negative reward. Okay. So this is, the beauty of this setup is that it's a fully, you can think of it as a fully simulated environment. You can explore in this environment and you can really test the ability of your agents to solve some of these tasks. So let me show you how the tasks are distributed. They're distributed across different sites, such as shopping, Reddit, and class fields. And there's also distribution, visual difficulty and reasoning difficulty. So there's about 15% of the tasks that are visually both. You have to understand visually what's going on. You have to do a fair amount of reasoning. And then there's easy and easy. Basically means that the visual representation is easy, and probably solving the task is also easy. It's just a few clicks that you need to do, the few steps that you need to take to solve the task. Okay, so let me show you some examples of what these tasks look like. Some of these tasks are fairly difficult, but humans can solve them. So let's say I give you these two images and I give you a task. Please add to my shopping cart all the items from this page that can connect these two devices from two images. So here I have to sort of understand that this is our J45 jack. And this is, probably one of the latest laptops that has USB-C. So what I need to do is I need to find USB-C hub, right? The hub that connects USB-C to a whole bunch of other inputs, including this Ethernet cable. What's interesting is that, humans can solve these tasks, some of these tasks, but it shows the level of the difficulty of what you need to do. Let me show you how you actually need to solve this particular task, right? I give you the task of buy me the cheapest color photo printer and send it to Emily's place, as shown in the image. And you can see this image is upside down. So this is the address that I need to send it to. So the sort of a visual system needs to understand that this image is upside down. So I need to rotate it 180 degrees and then do some form of optical character recognition to recognize what the address is, right? So we specifically designed making it a little bit harder for existing systems, but humans have no problem solving this task. But just to show you what you need to do to solve this task, what steps you need to take, you need to start at the home page. You need to navigate to the printer category. So you have to click on office products and the printers and accessories. You have to sort by descending order. So there is a sort button here. So I have to find it, sort. You have to click on the cheapest printer, right? Which is this printer that's available here. You have to add it to the shopping cart, right? And then you have to proceed to the checkout. So you have to click on a few buttons. Then you have to add the address to send it to the Emily place. So you have to fit in all the correct information that you have to extract from this image. And then you have to place the order. Now, if you look at this whole sort of system, it's not an easy task, right? The agent has to understand what it needs to do, what its objectives are. It needs to go and execute these low-level actions of clicking and filling in the information, right? So it's not an easy task. Well, here is another example. Navigate to my listings of all black bike and change the price, including the description, to $1 more than the cheapest bike on the site, right? So what that means is that I have to go through this site, this is Craigslist, find all instances of bicycles that look like this that I'm selling, find what they're selling for, what the prices are, and change my price to whatever the cheapest price plus $1, right? And that sort of requires, for humans, it would require a lot of mental sort of, set, because you have to search through a lot of things. And this is where AI can actually do much better. Or, find me the cheapest black Toyota available and add a comment to offer 500 below the seller's price. So imagine a system that actually finds the black Toyota, makes an offer for the price, and eventually in the future, these agents will probably be able to negotiate, prices and things of that sort. Right now, we're just basically trying to build a system that finds the right information and makes a posting on its own, everything sort of autonomously. And for that, we really need to build very good visual language models. If we look at sort of text, such as HTML, it's just such a hard thing to do. It's cluttered with unnecessary information. It's long and confusing content. And what we've been sort of advocating is using visual language models plus set of marks. So there is a way to sort of parse the website with the boxes, and those boxes would identify items that you can click on. So it's a specific representation of, think of it as parsing what's on the web page. And so, for example, here, if I'm trying to get a particular task, my low-level action here would be to click on box 33 because I'm trying to add to the cart, and this is the cheapest printer, so I have to click on this, right? So you have to sort of understand visual representation as well as the low-level action. Here I'm clicking on, button 33, right? I'm clicking on specific thing. And what's interesting is that if you look at a lot of existing state-of-the-art models today, right, models that are already relying on text only, they basically do really, really poorly. You can look at the multimodal systems. Multimodal systems today, for example, GPT-4, 4V, which actually has a very good capability of processing visual information, of Gemini Pro, which is the Google sort of system. You sort of can see that, GPT-4V does the best, but, other models are not doing so well. And if we use sort of, images instead of marks without actually accessing HTML, GPT-4V does reasonably, a little bit better. And Gemini Pro, which is the Google system, does does worse. But what's interesting about these systems is that, human performance is 88%. Right. And that's sort of very interesting thing is that even the state-of-the-art systems today cannot solve these tasks, primarily because a lot of them require a lot of form of reasoning and kind of like clicking and understanding. And humans are pretty close to, to getting to some optimal behavior. And again, this is sort of shows you the big gap in performance of what these systems, today's systems. And I think there is a lot of room to go to actually build systems that can do a lot of these tasks. I wanted to show you one example of GPT-4V that actually is using set of marks as its input, as a visual input, solves a particular task. So here I give you the image, the visual image, and I tell you, I don't like the author of this image from one of the posts in F memes. Can you help me block them? And so the agent has to go, find a particular user, click on things, navigate to a specific memes forum. You have to go to the profile of the user who posted this image. You have to click on the block button and then confirm the blocking of the user, right? And imagine systems that, this could be pretty useful, right? I give you some visual input, and here it's a specific task where I say, I don't like this particular user blocked from my feeds. And, you have to go through a set of, low-level actions to go and execute that. And we think that the VisualWebArena is a step towards building general purpose agents. Of course, the tasks that we're designing might not be very consequential, but these tasks are simpler as current large language LLM agents don't even work on these tasks. The long-term goal for us is to automate productive, economically viable tasks. The medium-term goal, what we're doing right now, is we're actually looking at some open-based simulators like OpenOffice for benchmarking and training computer agents that can sort of operate in that space. So for example, I would like to have a system that says, add a slide summarizing the trends of the Excel spreadsheet, right? So the system has to go look at the trends, understand the visual information, and then create a slide, PowerPoint slide, or Google Sheet slide that summarizes the trend. Or, create me this presentation based on the content of this report. So for example, right now I'm talking about specific paper in the VisualWebArena, but it wouldn't be nice if I just gave my paper to the AI agent and tell it, give me a set of slides. And it would go understand what these slides are. It would make a coherent story and generate me a set of task, a set of slides for me, right? So I think these sort of systems should be possible. I think maybe not in the near future, but that would be pretty exciting, right? So it's no longer systems like GPT-4 where I give you the question, it gives me the answer. It's actually a system where I give it a task, an objective, and it goes and executes it for me. So it almost becomes like my personal assistant, right? And so in principle, we could simulate a lot of tasks. There's something database that's basically lists all the jobs performed by workers in the US, created by the US Department of Labor. And I think that a lot of these tasks potentially could be automated. Of course, we also sort of thinking about the multimodality becomes very important. Just like we've seen with the visual agent, or sorry, the physical agent navigating in your house, visual understanding is very important. And visual understanding for these virtual agents and grounding these visual agents becomes very, very important, especially for tasks involving, Excel, Photoshop, or whatever you do on the web. Right, to be able to develop these strong general agents, you need to be able to develop very strong visual language models, or VLMs. Okay, so just to show you maybe a couple of more examples. Let's say I give it a task. We're trying to analyze when these agents fail. Buy me the highest rated product from the NS Switch. NS stands for Nintendo Switch. Category within a budget of under $60, right? So GPT-4 behaviors, it sort of goes and it stops, right? It just doesn't complete the task. On the other hand, you want to have a desired behavior where you actually go through a whole bunch of actions and then complete the task, right? So there's been a lot of work in the last year and a half on, systems like React, chain of thought prompting, there's WebGPT, there's Mind2Web, Tolkien GPT, Toolformer. So it's just different ways of using these large language models and trying to build the agents. And what we've been doing, we've been building agents that have three components. So the first component is high-level planning. High-level planning basically means that if I give you the task, what is the sequence of high-level plans or subtasks that I need to execute? Much like what we saw in the previous example of visual instruction following, where I give an instruction, I have to define sub-objectives that I need to solve. There is observation parsing. Given the observed data, you do some form of parsing of the images or the text or whatever that representation is. And then there is a set of low-level actions. And low-level actions, like clicking on specific things, or in the physical AI, it's actually, moving 20 centimeters forward or turning 20 degrees to the left, right? So these are sort of, the system is applicable for physical AI or virtual AI. Right. And it turns out that high-level plans becomes very, very important for long sequences or for complex objectives. Right. So for example, if I'm trying to buy some high-rated product from beauty and personal care category within the budget of under 20, you can say, well, step one, navigate to a specific website, requires one low-level action. You sort based on the rating in that category, requires two low-level actions, it requires selection and sorting. Then, select the item under $20 requires one low-level actions. And then buy the selected item requires three low-level actions. You have to add to the cart, you have to proceed to the checkout, you have to click on the ship. Right. So again, you can think of these high-level plans as a way of providing weak supervision to your model. Right. And so how do you generate high-level plans? That's a sort of research on its own. What we found is that, a lot of times people will say, well, I'll just go to GPT and ask GPT to do it. And GPT models do kind of like okay-ish, but what we found actually getting human annotations, at least a few human annotations of how to solve these tasks, actually improves performance by quite a bit. Right, so this notion of generating high-level plans or objectives is actually very much open area of research. Okay, observation parsing is also a lot of work. We're using set of marks. That people are using accessibility trees, different ways of encoding information becomes very important. How do you parse the representation that you have? Right? And also generating low-level actions. So what we've done here is we've been using a particular data set called Mind2Web dataset to actually train a model to execute low-level actions, such as clicking or hovering or typing. And then we would take it and transfer that low-level action module into the WebArena environment and test how well it does. But this sort of low-level action, you can share it and you can transfer it across different tasks, across different environments. For example, if you try to search on Amazon, it's the same sort of low-level action as you're searching on, I don't know, Best Buy or some other site, right? Just to give you an example. And again, just to show you that with good enough sub goals or with good enough sort of high level plans, these large language models actually do reasonably well, right? So if you're giving it more information of what it needs to do, a lot of times it would complete the task. And GPT-4 does the same thing, right? If I sort of give it just the goal, it's stuck, it doesn't know what to do. But if I break it down and tell it what it needs to do, it can solve the task correctly, right? And again, it's not surprising because I'm giving it more information. So figuring out what these high-level plans are is important. And that's true even for physical AI agents, where if I give my agent, hey, go and make me coffee, if I can break it down to subtasks, so first navigate to the kitchen, find the coffee maker, and sort of do these pieces, the agent can succeed. And just to show you, trying to use GPT-style models to generate these high-level plans, they sometimes becomes too ambiguous. It's hard to understand, but human annotation becomes very important. Here, what we found is that we have a bunch of grad students. Grad students have a few annotations, can actually improve accuracy of our models quite a bit by just having a few high-quality annotations. One final thing I want to point out is that in these sort of settings, in these agents, we can also sometimes when you're generating these low-level actions, sometimes you either get confused or you do the wrong thing. And so what you can do is you can try to search over possible low-level actions. So in this case, it becomes what's called a Monte Carlo tree search. Each node can represent, let's say, a website with its own web content. And the edges would represent going to the next web page, taking the action and go to the next. And so you can design sort of heuristic functions to do the pruning of the actions that are not likely to lead to your goal. But this becomes very much in line with, I'm sure many of you have heard about Monte Carlo tree search or examples like AlphaGo. And so these kinds of ideas can also be leveraged in this setting, right? Where if I look for a specific task, what's the price configuration of the tree I bought in 2023? It requires multiple stats to search over multiple past orders and so forth. So you can sort of try to build a system that can searches over different instances and sort of clicks on different things and tries to do pruning until it finds the right answer. So there's a lot of work that can be done in the space. And of course, it requires visual understanding. It requires language sort of understanding, and it has this notion of executing actions or taking actions. Okay. And so what's interesting, again, when we look at these models, some of the common failure modes is that these models oscillate between two web pages. Sometimes they get stuck. Models typically get confused over long horizon. I give it a task and it requires sort of, which is a common problem in decision-making and reinforcement learning, being able to solve problems of a long horizon is very difficult, right? Because it requires me to execute a lot of actions and the probability that I'm going to fail just grows. And agents tend to stop exploration execution too early, right? And part of the things that we're working on is trying to leverage the simplified representation. Visual representation becomes important to even store the history of states that you visited so far, to be able to do search and to be able to do plan. And I think that this notion of search and execute a coordinated, and coordinate multiple instances in parallel would actually be quite useful, right? So you can imagine the future agents that can actually do and in parallel execute a whole bunch of things to be able to find or to solve the task that you give it. And of course, we're also working in a space of, asking for clarification confirmation, which comes down to estimating uncertainty. If the agent is uncertain about certain high-level plan or certain actions that it's taking, it can come back to the user and ask for clarification. Okay. Finally, this exact same structure goes into, we've been looking at robotic manipulation tasks, much like robotic navigation. We can also look at the systems that can do manipulation. And again, as I've mentioned before, the overall structure remains the same. There's a high-level plan that sort of tells me what I need to do. There's observation parsing, trying to look at images in depth and do some form of semantic segmentation. And then there are low-level actions that you actually have to do to execute a task. And again, all of these three modules can be trained separately and are exchangeable. So you can, in principle, take these modules and apply them in different environments. And this is one of the recent work that we've been thinking about. Again, there is a planning module that uses large language models to plan what you need to do. There's a parsing module, a sequencing module that sort of tries to solve a particular manipulation task. And then there's a low-level action module, which is, again, some form of reinforcement learning agent that actually tries to execute low-level actions, right? And, these kinds of systems, much like in the virtual space, they can solve, long horizon robotic manipulation tasks, right, with pretty high success rate. And again, the reason why I'm showing to you is there's a lot of transparencies, between virtual agents executing on, web and virtual environments, as well as agents that can actually, operate in the physical world, like grabbing items and doing some form of manipulation. Right, here's a system that does motion planning, does local policy, that sort of tries to solve these manipulation tasks, right? And here's the agent that's trying to do the assembler, right? So again, same story holds, even though the task is very, very different from, navigating, buying stuff on the web. You're actually assembling a furniture here. But the underlying sort of ideas are very much similar. Here's the agent that executes a lot of different tasks, like opening, doing something and executing a whole bunch of tasks, right, with this virtual arm. And again, I think that in the future, you're going to have agents that can move in the environment, as I've shown to you, agents that can manipulate objects in the environment, as well as agents virtually that we're going to be doing a lot of tasks for you. And one of the interesting takeaways here is that, this notion of connecting large language models to low-level control becomes fairly interesting, right? So LLMs are very good at high-level planning or figuring out sort of, some form of semantic understanding of just because, they get to see a lot of text. But connecting them to the low-level control, actually executing low-level control, both physical and virtual, like clicking or grabbing something, becomes very, very interesting. So this connection between these two. And also low-level control needs to only be learned at some local low-level interactions, like learning to click on a search or on a search button or grasping a silver nut, right? So these low-level controls can be pre-trained and can be shared across different environments, across different settings. So that actually gives us the ability to, the hope that these agents are going to get smarter and smarter, and we'll be able to solve a lot of tasks for you. And one last thing I wanted to mention is AI safety and robustness. AI safety and the ability to build these systems that are robust becomes fairly important, especially once we start moving to, the space of autonomous systems that can take actions and can take a series of actions to achieve a particular goal, right? And that's actually one of the areas which is actively being researched on, is how do we make sure that these agents are robust, and how do you make sure that the agent doesn't go and just buys, adds to your cart and ships the whole bunch of things that you don't want, right? So things like this is becoming very important. I think that we're still very early on the agent space, both in the physical and AI. But in the next 5 to 10 years, we're going to see more and more systems that are not just question answering and just giving you the answer, but systems that actually take actions and solve tasks for you. So on that note, thank you very much. And thank you for giving me the opportunity to talk to you today.
Thank you, Russ. It was an excellent talk. And we came face to face with the, I should say, the kind of power of self-supervised reinforcement learning. And of course, their efficiency in addressing tangible image-based robotic manipulation tasks over the real world. And some of the tasks are even delineated by a single goal image, introducing post-training. We also got some very good demonstration around the VisualWebArena. And I believe that's a very critical lacuna in the existing evaluation landscape for autonomous agents. So now I would like to request the participants, if you have any question, this is your time to ask directly to our honorable speaker. Faizan, let them unmute and ask if they wish.
The participant can unmute themselves and can ask the question.
So I see
Yeah.
there is a question in the chat. So Ras, can you just check the chat where there is a question from Nitin, I guess?
Let me just look at the chat 1 second. So there is, okay, thank you for the gainful curiosity. Please explain how the system manage associating action moving. So, okay, so one question that I'm seeing here is, what is the gainful curiosity? Right. So the way that you can think about gaining curiosity is sort of a way of trying to get definitive knowledge. So you can think of the system, imagine the system that, moves around and recognizes certain objects. And it sort of says, I think that this is a cup, or I think this is a laptop. And what we can do is we can basically look at the confidence of that recognition and say, okay, if my agent moves around in the environment, how many confidently detected objects I can find, right? If I find a lot of objects that I'm confident that those objects are detected, then that means that I have high reward. If I move around the environment and I don't detect anything confidently, that means I have small reward. So I'm incentivizing my agents to move around and look at the objects from specific viewpoints and trying to sort of identify objects that I can, reliably detect. And that's sort of the gainful curiosity, right? It avoids this issue that we've had before, that the agent stands in one room and just turns around and doesn't do anything, right? So that's sort of the gainful curiosity. Okay, so let me ask, there's a couple of other questions. What are the future direction research domain of LLMs? So I sort of have my own opinions of what the future domain of LLMs, large language models. I personally most excited about what I've talked about, which is the agent world, which is large language models plus visual representation, multimodal large language models that can actually take action. So, solve tasks for you. So for example, I can give it a paper and say, create me a set of slides. Or, I had this, like, my internet went down yesterday and I spent 2 hours on the call with my internet company trying to figure out how to fix it. I want to have an agent where I tell my agent, call my internet company and figure out why my internet is not working, right? And I think in the future, we're going to have these sort of LLM agents, or maybe there's going to be something else that can actually call my internet company, talk to them, probably in the bot on the other side, figure out why I'm having the problem and fix the problem for me, right? So I think that that's the space that I'm most excited about. But beyond that, I think, there is also a lot of work in LLMs where you're trying to improve reasoning, or you're trying to kind of give it like factual knowledge so that you avoid hallucinations. A lot of times these large language models will say something that's not right. So that's one domain of research, very important domain of research, how to get rid of hallucinations, because sometimes you can't trust the output of these models. And the third sort of, research that I see, where I see a lot of my colleagues work on, is this notion of safety and alignment. Safety, basically, how do we build the systems that they don't say or do something that's, you wouldn't want them to do? Right. So for example, how do you make sure that the agent doesn't take actions that are, that can lead to bad outcomes? Or how do we, prevent hacking these systems? Because a lot of times with these LLMs, I can give it a specific instruction and it will tell me, something bad, for example, right? And that becomes particularly important, as I've mentioned, in the space of agents, when these models can actually take autonomous actions. So that's sort of where I see research happening in LLMs. And of course, there is also a lot of work, maybe not on the machine learning side, but also a lot of work happens on how do we do fast inference in these models? How do we, train them faster? How do we, there's a lot of kind of like software, engineering efforts to be able to scale, which is very, very important. Right, so we can scale this, continue scaling these systems so that we can
That was a very complete and concrete answer, I should say, for this moment. And thank you again for elaborating on this. By the way, I just wanted to ask you that in several, autonomous agents or on the internet, there are text-only language models are still there and very active in enterprises. So how does VisualWebArena specifically address the limitations of such text-only LLMs? Not the multimodal ones.
Just text only. Yeah, so there is, the VisualWebArena is trying to go to the multimodal space. There is a web arena, which is sort of integrated within VisualWebArena that only operates on the text space. So you can kind of like test these models as well to see how well they do. And again, these models are still like, even GPT-4 is not very good, right? Even in these settings. But I think that one of the things that, I see that happens in big companies is that a lot of them are looking into that space. And a lot of them are also trying to build their own sort of evaluation environments, evaluation frameworks, because part of big challenge of these things is that I can give it my paper and ask it to generate a PowerPoint presentation. It will generate maybe something for me. How do I know whether this is good or bad? It's very hard to sort of say this is good, this is bad, right? And so this notion of potentially some form of reinforcement learning from human feedback or some version of it where someone looks at it, but to be able to scale it up, we need to build evaluation like simulators that basically kind of guide us towards like this is a good state and this is a bad state. So it's a fascinating area of research, and it's just opening it up. It's just being opened up right now. So there's a lot of work I think that needs to be done on evaluation, on building better models. This notion of understanding high-level plans, executing low-level actions, both in physical and virtual. So I think the next 5 to 10 years are going to be amazing.
Still now there cannot be a universal gold standard for the sort of outputs they generate, as you were saying, very rightly. And companies have their own standard and internal ways of evaluation, of course.
Yeah, that's right. That's right.
If there are no more questions from the participants, let us heartily thank Ruslan for this wonderful and very illustrative sort of lecture, which I believe every one of you got something to take away. So thank you very much, Ruslan, for joining us once again. And we hope to wrap you up in some of our future events too. Hope you you find some time to visit India and come to Indian Statistical Institute, which is a very pioneering sort of research institute in statistics research. And if you know D-square function, the Mahalanobis distance function, so
yes,
was founder of this institute.
Wow, that's amazing. I definitely, I will make sure at some point. I would love to come. We have, at CMU, we have a lot of amazing students, PhD students, master students coming from India, from your institution, and from IITs. It's great. Yes, and by the way, for the audience here, if you have any specific questions, feel free to email me. I'll try to respond. And again, thank you very much for
that's very kind of you. Very kind of you. Thank you, and have a wonderful day ahead.
Thank you.
Thank you,
Bye-bye.
participants. Good night to all of you. Bye-bye.